And so I'll be presenting the work we did as part of the EU project called SODALITE around optimizing AI training deployments using GRAH compiler and containers. How did we go about doing it? So I think before we start, I think we have one of our great machines, KRAH machine at ICM. Okay, knows, and is a KRAH XE40 machine, which has been a very good success for KRAH and now HPC as well. This has a more than 1,000 compute nodes of Intel Xeon as well, and a very good Aries interconnect, and very lustre parallel file system. So I'm part of the HPE EMEA Research Lab. Used to be called SIR before, for people who used to know KRAH. This is focus on HPC and AI in general. I think we provide deep technical collaboration for HPE and customers to work together, focusing on new technologies, where we can work with the customers to drive HPE products in the future. And this is mainly focused on long-term technical relationship, where we can work with the customers and understand their requirements, and then work with the products. As a team, we are a group of more than 10 people. We have a strong research interest around the memory hierarchy, data movement and workflow optimizations, compilers and mathematical optimizations, and also how HPC, how does it come together with AI and big data, and how it works with cloud, with all these new paradigms coming into place. This is of huge focus as well. As a lab, we work on 3 different models. At least we work with the customers. One is Center of Excellence, which really comes along with our support, and we work with the users of the supercomputer to enable them to use it very well. We do value add projects where we work with customers to add value to one of the projects by working with them actually closely. And we have been involved in a lot of EU Horizon 2020 projects, which I'll come to it in a bit, which is also our big focus now. To say, I think these are the 3 center of excellence in our lab we work on. Archer. Archer is the UK's national supercomputing facility, which supports most of the users in UK. It is a KRAH XE30 machine with close to maybe 2,000 nodes. It is being replaced by ARCHIT 2 now, which will also have, I hope, will have a center of excellence. We focus mainly on I/O analytics, monitoring, application tuning, and I/O performance optimizations in Archer. This is one of I/O being one of the main focus here. Cost is one at UAE. Our COE, there, the Center of Excellence, focuses on working with customers on asynchronous tasking, deep learning for bioscience, and a lot of other projects as well, actually. One of the recent success we had with Center of Excellence is the GW4. This is an ARM-based machine. This is a joint ARM and KVM partnership. We provided a machine with different architectures so that it can be used for performance comparisons across different hardware. We provide a software environment around ARM, which can be easily used for applications. We had many applications ported to ARM ecosystem and tuned for it, and this has been presented at SC and ISC in the last few years. Moving on, our lab has been working on these European projects. So this is just a summary of what we are doing. Expertise, I've shown listed all the partners in most of the projects. Expertise is a project which is funds the Marie Curie early stage researchers. We have a researcher who's focusing on memory hierarchy. Master projects looks at workflow optimization and how to orchestrate these workflows. And actually, Epigram HS mainly looks at memory hierarchy, how data can be cached, how to do tiling when application accesses it, how do we manage data in a heterogeneous memory or heterogeneous system, how to do data movement and things like that. SODALITE is a project which I'll describe in detail in next few slides. For plan for us, we are looking at data movement using different transports and how containers can be used here. We have a different range of partners. And we also work with PhD programs like Europlex and Vinova. We work with them and closely collaborate with them actually. So one of the projects I'm going to describe, at least, is the SODALITE project, the work we did as a SODALITE project. Why do we need a SODALITE project actually? As we see, I think there's multiple ways of application can be deployed. There's a lot of variety now, a lot of heterogeneity in the software environment. There's a lot of HPC in-premise, a lot of public private clouds, and a lot of data centers across the world actually with different environment actually. And getting your application deployed at different environments and porting them from one to another, this becomes a huge challenge not only for developers but also for people who are deploying it and maintaining these applications. And we need to also ensure that once we deploy at different places, we get a very good performance out of it as well. For example, we had a talk where I think we have a new center coming in Ethiopia. We have a very low energy footprint. Suddenly, you want to move all your applications or your from let's say UK to Ethiopia. So this can be enabled easily. So SODALITE aims to provide a lot of tools which will enable a simpler and faster development, deployment, execution of all your applications or most of applications in a heterogeneous environment like HPC or cloud actually. And this lists our partners who are working with us actually. So what does SODALITE, why SODALITE? Why do we need SODALITE? As I mentioned, I think we need effectiveness. I think we need a very good effective runtime implementation of an abstract model to a deployed application. We'll be able to deploy an application pretty easily. People should be able to optimize the deployment. Application should be optimized to the particular target you are trying to deploy it. And your way of deploying application be very flexible as well. For example, currently we saw that the ARM, Intel GPUs, x86 FPGAs are coming in. There's a lot of different technologies out there, and we should be able to flexibly adapt to these different hardware backends. And also, we need speed. You need speed of doing development and packaging and deployment, and make it very easy to deploy across heterogeneous targets. So this is the overall architecture. I won't go in detail, just to show what we are trying to achieve as a whole. We have a modeling layer which tries to model application, different infrastructure targets, and how the performance maps and everything. Then we have a infrastructure code layer. All the deployments are done as an infrastructure as a code, so that the modeling layer models all of them. And then this is we use a Tosca-based standard here to wrap them as a infrastructure as a code, and then this is deployed using a SODALITE runtime layer. The 3 layers here. We have also APIs around monitoring, orchestration, verification, defect detection to enable all this. And we support different backends like Torque for HPC, OpenStack, Kubernetes. There's a variety of solution coming around in the market, and SODALITE will be able to support all of them in the future. So I think what we aim to produce at the end of is an pattern-based abstraction library, which will have models for application, infrastructure, and performance, and which will then translate into an infrastructure as code based on Tosca standards. This will facilitate that this can be deployed across different vendors, since it is standardized actually. And we have a deployment framework which will enable static and runtime optimization of application on a specific infrastructure. So in all this is a bigger project with a lot of partners, and HPE in particular is very much focused on optimizing an application actually when it is getting deployed. So what are the performance requirements of an application which is getting deployed? Actually, we'll look at it. Actually, we can't look at, for example, optimizing any application on any target. This is simply out of scope. So we try to focus on 3 different type of application which are being heavily used. One is AI training and inference, big data analytics, and we focus on traditional HPC application, which uses MPI, OpenMP, OpenACC. Then with these three application domain, I think we can say, let's say most of it will map to most of the HPC application out there. Then we have a lot of configuration, how to optimize this application, and we develop a performance model around this application. If we have this information, how do we very well optimize this application when it's getting deployed on a heterogeneous infrastructure, which can be HPC or cloud, which might have a different compute, as I said, CPU, GPU, FPGA. Obviously, I/O is getting a huge thing in performance, and the luster, SSDs, object stores also play a different role in how this will be deployed and optimized. Interconnect network, especially Ethernet, InfiniBand, there's different variety here, and we have a slingshot from HPE GRAH, which is coming into the market with huge futures there, and different schedulers for HPC like Stark and Slurm, and the ever popular, becoming more and more getting popular, Kubernetes and OpenStack for cloud. So this variety of environment here and variety of ways to optimize it and how to deploy it, and we need to try to understand all this complex picture and try to do it for it. And we can't depend on an AI scientist or any simple data scientist or any scientist to really figure out all this for himself. He can't be an expert in all this. So once he provides an application and in a framework, then an application optimizer should be able to optimize it and deploy it in a efficient way. So in SODALITE, what we are looking at is a SODALITE framework in which we have an IDE in which an application, a user can specify what are the optimization he wants to enable. For example, there are many application tasks, and we have an optimization deal in which you can say, I'm running an AI training framework, go ahead and optimize it for this graph compiler, tune these parameters for me. He will mention as that. He will select some of the optimizations he wants to enable, and then we build an optimization recipe for a particular target based on the selected target, and then we go and optimize it. The optimizer will go and take the optimization and build an application, and then in a container. I'll go, I think a container, I'll go to why we need a container, but I think most of the solution in SODALITE will build an optimized container, which can then be easily deployed for performance. So this is the architecture of the application optimizer component we are developing as SODALITE. We have we are supporting 3 different application types, which should be written in a high-level API so that we can understand it. Along with it, we get the application configuration and inputs, and this is being input to the application optimizer component. We need to understand the performance model of the infrastructure and the application. These performance models are developed based on offline runs, and they are all stored in a model repository, along with the optimizations you have selected, which is stored in the recipe. So once these information is available, and also we have all the containers, optimized containers we have built already in our image repository. So once this configuration comes in, then application optimizer will map based on this optimization, this repository to use and a container to use, and these are the settings to be enabled. And then it will go and edit your job scripts and then build an optimized container so that this can be readily be deployed by the your environment actually. So I'll give you an example. For example, we have an AI training example in which a data scientist, he writes his code in a high-level API like say Keras or inference, let's say ONNX, which is a standard for AI models. And then he gives us the inputs, the configuration, what are the optimizations to enable as his inputs. This is how a data scientist will be using the SODALITE IDE. And once he inputs all this information, then the infrastructure as a code component will kick in. Then based on the optimization select, we will select a particular AI framework, and then we can go and select the different libraries, target specific libraries and different compilers to use. And then we'll build a container for him, which can then be directly deployed to a cloud or a HPC environment. You see how much things we can really abstract it as scientists, so that most of the things he don't have to be aware of it. But once he uses this framework, and the application gets optimized automatically, and it runs at a better speed, which results in a better saving for everyone and also savings in time and cost. So why do we need containers? Is a question I think a lot of people will ask. Actually, why not do something else? I think this is one of getting more and more famous as a well-established way of packing applications with all the dependencies, so that you don't have to worry about a lot of things. Actually, moving application from HPC cloud with different environment, and then trying to install all your packages, trying to all your getting your dependencies right. This is going to be a very difficult. With containers, you get everything at a go. You pack everything together. You just move your container, and then it works on both HPC and cloud actually. And compared to a virtual machine, actually, where you virtualize everything, this is faster to deploy and this is faster to run actually. And we have seen that this is popular with HPC applications, where you prepare and you test your container in your laptop, and then you can run on a large supercomputer. So it's getting very useful actually. And but for HPC applications, there are a lot of requirements around performance. You want to not lose any of your performance with using containers. Again, security, where you don't want to others to see what you're doing and access your containers actually. And again, compatibility, and we should be able to still use your MPI, which is very famous, and your GPUs for AI training and network, and get very good performance at the end of the day. We explored multiple container technologies which are out there actually. I won't go into it in detail, but I think there are a lot of pros and cons. Docker being pretty much a standard, but has issues around security and performance. There are also new technologies coming up like Shifter, Charlie Cloud, and Saurus, but they're all still in a starting phase with not a bigger, larger community base. We understand that I think Docker image format is very good, whereas Docker as a technology is not still suitable for HPC. But I think Singularity is a solution which is getting very famous for HPC, and it looks just made for HPC. So I think you can build your Singularity images, or you can use Docker images in Singularity after converting them. There's a huge, large community, and I think this is going to be very famous or very good for HPC actually. So how do you build a Singularity container? It's pretty simple. You just have a definition file where you write your what is the multiple your things to build your container, and then you say Singularity build. You don't need root permissions here, and then you do has your fake root permissions. You build a fake root, and you get your Singularity container. This example shows how to build first a Ubuntu image, and then on top of that Ubuntu image, we build a TensorFlow container. Once you build this container, you can then move it across and run it anywhere. So let's look at AI. AI, I think, I guess most of you know about AI models. I think so. When you are trying to build the AI, actually, you can optimize using multiple ways. One of the better ways of doing optimizing them is graph compilers actually. Why do we need graph compilers? Because AI models usually are represented as computational graphs, in which there are nodes represents the tensor operators and edges represents the data dependencies between them. And these models are written in Python or any Scala or any languages, but these are then converted into an intermediate representation, and these are then optimized for different hardware backends. These graph compilers, which sit in between the AI frameworks like TensorFlow, PyTorch, and everything, they usually do a lot of optimization around operator fusing, reducing the memory latencies, and mapping those kernels to hardware primitives so that they can run pretty fast. Also, these graph compilers can map most of your calls to optimized libraries, and which is very good. Some of the times, what happens is that you write your own kernels for AI training or your graphs, then this doesn't get supported. So in this case, graph compiler comes in, it just builds an optimized kernel for you out of your graph actually. So if you look at, there are multiple frameworks for AI, and there are also multiple graph compilers that are coming into picture for AI actually. On this table list, what are their support for different frameworks and graph compilers? On the left, we have on the left column, we have many different types of AI frameworks out there. On the column side, we have different uh, graph compilers out there: XLA, tensor comprehension, TVM. ONNC is the open standard for neural network compiler, as a GLOW, Intel ngraph, Applied ML, and TensorRT. This table, T mentioned that there is support for training or AI training. I supports that this graph compiler supports AI inference. N support there is no support, and some tools might require rewrite, and some of these are getting merged all the time actually. So if you look at this table, actually, there's a lot of support for AI inference, which is using a training network at the end of the day to do some actual inference, actually. Whereas training is a very long process where you have a lot of data and labels, and then you train it for a long time, actually. This is a very compute intensive work, AI training, and then it needs a lot of HP resource, and optimizing them is very important. So we will look at some of the famous graph compilers. At least we look at XLA, try to look at GLOW and Intel's ngraph, and how this performs on a HPC machine when packed as a singularity container, actually. So once we pack them as a singularity container, we can deploy it in an optimized way once we know how they perform very well. So for our comparison, actually, I'm going to use an simple MNIST convolution neural network, I think, which most of the people are aware of. But to make a fairer comparison, we need to have the same network with almost similar parameters so that we can make apples to apple comparison here. So this shows the at least the simple network we are trying to use for MNIST database, which is all digits 1 to 10. Simple images uses a 2 convolution. There's a max pool, and then a dense layer, and then a dense layer again, and we have a softmax. And for all your test cases here, we use the same batch size, number of epochs, same number of image size, and the total number of parameters is all the same. So this should be the same, so that when we use different AI frameworks, or still we get the same, we can compare apple to apple performance. We can compare the performance, and it's still correct, actually. So what we did, we went ahead, built containers for at least the 4 major AI frameworks out there: PyTorch, TensorFlow, MXNet, and CNTK. And we compared the performance that for this MNIST alone, running on a single node of a CPU with Intel Sandy Bridge architecture, actually. With TensorFlow, you have to look at, then there are 2 different TensorFlow ways of writing it. TensorFlow 1.4, all 1.x had a different way of writing code, and they have completely changed it in TensorFlow 2.1. So as you can see, this is the workload time. Anything higher is bad, anything low is good. This is going to be the way we're going to use it in all the slides, at least the result slides. So see, PyTorch and TensorFlow 1.4 around same. MX doing pretty good with around 300 seconds only. CNTK is completely not optimized for CPU, which they say in the documentation as well. So I think still pretty bad. But TensorFlow 2.1 doing a very good job with the latest version. Seems to they have improved a lot compared to the TensorFlow 1.4, which was a previous iteration. And it runs very fast, and it seems to be tuned very well for our Intel architecture, x86 architecture, actually. Moving on, actually, what we can do is that we can build these frameworks. Instead of doing a pip install, we can just build them from source, which means that you get target specific optimizations like AVX2, your SSE, and other bits where your kernels are directly mapped to your hardware specific components, actually. So we built around containers for 2 famous networks, PyTorch and TensorFlow 2.1, and then we ran these again, same network, same conditions. As we can see, a PyTorch it takes around 396 seconds, whereas if you build it from source, you build a container, and you with that build from source, then you get almost 50% speed up. It runs pretty fast. whereas a TensorFlow seems to be already very well optimized for x86, as I mentioned, and you get a still improvement, but the improvement is not big actually. TensorFlow has recently made a lot of improvements around just optimizing for x86 in general. But again, if you move to ARM or other different type of processor types, then this building, custom building from source, I think will give you at least 10 to 15%. This is the expectation, at least from our studies. Next, moving on to using graph compilers. On top of this, actually, we are trying to compare the graph compilers here. This is again using TensorFlow 2.1, using the same network everywhere, actually. So if you look at this, actually, I'm trying to compare the performance across without anything. The TensorFlow 2.1 runs pretty fast, but when you enable XLA without the source build, it runs pretty slow because there's a lot of overheads on top of it. Because you have to compile the network and then create all these kernels. So this is currently it's still a not good solution for smaller network, it looks like. But once you do a source build, it still improves the performance compared to a non-source build, which is at least from this comparison actually. Again, this is repeat again. I think we still, this is not good performance. Improve this performance really degrades, and this is mainly due to the initial JIT compilation, which takes its own time actually. ngraph is a compiler which is developed by Intel actually. This is supported in TensorFlow. We again compared the performance of using ngraph for TensorFlow. TensorFlow, you can write code in different ways. One using Kira style code and one using simple old style TensorFlow code actually. So we compared both these different code bases with enabling ngraph. As you can see, TensorFlow 1.4 runs around 250 seconds, but enabling an ngraph gives you around 15 to 20% speed up. Whereas if you use a Keras type code and you enable ngraph, it just runs slower. So Intel's ngraph is still not integrated well into the latest Keras style coding for TensorFlow, whereas this works very well for older style code. Looks like they have not yet moved their optimizations across, so we have to wait for it. But in general, we get some very good speed up here, close to 10% on the TensorFlow 1.1. Moving on, I think we looked at some bigger networks. Obviously, we didn't get very good performance out of the XLA, so you looked at ResNet 50, which is a very good successful network used for image recognition. This network has a lot of back connections to enable a lot of feedback across the layers actually. So looking at the performance of the ResNet actually is pretty preliminary. We see there's a lot of, this is the timings for startup and training steps for TensorFlow 2.1 and with TensorFlow 2.1 enabled. We see a huge increase in the startup time. As I said, these networks take a lot of time to build. You have to compile the framework to the particular target architecture. So the startup time is almost double here. But once we move to a train steps, you get a bit of optimization, but this still needs to be looked at, like still if it is a noise or you're just getting a bit of performance out of it. So we are still looking at this preliminarily. Again, we'll look closer at GPU's results as well in the future. So as we see from these results, we are getting performance improvement by just building from source and also using graph compilers. But in some cases, it's also not very good. We need to understand when to use what and how to deploy them. When you're deploying it, which will give you performance improvement and which is not, and then make a decision after when it is deployed. So in conclusions, actually, this deploying and optimizing AI training workloads for targets is very complex, and it's going to get even more difficult with the different architectures coming in. And SODALITE tries to solve this problem by providing tools for deploying and execution in such environments actually. And we have the application optimizer component, which is we are building, which will enable you to use this component to automatically optimize for a different target architecture actually. And as I showed you, actually, we can optimize this using different uh, graph compilers and target specific libraries, and then building them in optimized container so that they can be deployed across different targets actually. We had some success using this, and we'll be exploring this further in our future work. I want to acknowledge our SODALITE partners who has been building this framework, and obviously we are a small part in this great work. And our colleagues at the HPE EMEA Research Lab and our co-sponsor Intel. Thanks for sponsoring this talk as well. And thank you. I hope I finished in time.
Thank you very much, KARTHEE. We have time for maybe one or two quick questions. We are waiting for you to type it in.
I think yeah, we have a strong interest around Intel on API. I think TensorFlow currently has support for SQL, which is pretty much similar to one API. I think we'll be exploring that in the future, and also on how and also on building, for example, once one API is available, how to build different AI frameworks using one API once, and then how it can be optimized for different targets. This is one of the main things we'll be looking at as well. It's of huge interest to us. Yes.
Okay, we have a second question.
I think Slingshot is. I doubt it actually. I think it's going to be available as for GRAH, GRAH and HPE, our part of our hardware solution. That's my understanding.
Okay, I think we have running out of time. KARTHEE, thank you very much. That was a very, very enlightening talk. It's really good to know what is happening in the industrial research labs in collaboration with various academic groups. Very interesting direction. I'm sure that many of our participants were listening with great interest. I know for sure that several people are interested in results of your work.